Hello. Today we're going to do another in the series of what I call annoying statistical calculations, and today we'll be dealing with the beta distribution. Okay. Now, to remind you what the beta distribution is, the beta is, well, first of all, I should just tell you what the prerequisites for the talk are. The first prerequisite is that you should understand change a variable. Yeah, for integration in the plane. In other words, you should know what a Jacobian is, limit changes, etc. The second thing you should understand, you should know what the gamma function is. Now remember, the gamma function, you can define it as gamma of x is equal to the integral from 0 to infinity. Now we're using the real variable gamma function, not the complex one. In this case, your dummy variable is going to be y, x minus 1 e to the minus y dy. And for our purposes, we're going to concern ourselves with x, a real number greater than 0. It turns out that you can extend it further than that, but we'll content ourselves with this. And what you learn from this is that it's a result of integration by parts. The gamma of x plus 1 is x gamma of x. The second thing to note is that if k is an integer, that's going to be k factorial. And it's the unique logarithmically convex extension of factorial from the integers to the real numbers, to positive real numbers. And what that means is that it means if you take the log of the gamma function, you still have a convex function. The way I think about it is it makes it a little bit like e to the x squared, but it takes on these values at the integers and extends it in a nice smooth way to the real numbers. So it's a way of extending the factorials to the real numbers in a somewhat natural way. So you should know a couple of these little facts in order to understand what comes next. Now, the beta distribution, let's get to that. It's for the random variable is y. And it has parameters alpha and beta, real numbers greater than 0. And the distribution is this. F of y is going to be gamma of alpha plus beta divided by gamma of alpha, gamma of beta. Then you take y to the alpha minus 1, 1 minus y to the beta minus 1 for y between 1 and greater than 0 and 0 elsewhere. So that's what the beta distribution is. That's a density function. And this is important for Bayesian statistics. And it's often used when you're, when let's say you have either a binomial distribution or something like a geometric distribution, And your parameter P, the probability, is itself a random variable. And because this random variable takes values between 0 and 1, it works very well for P. And it has a nice property, which is beyond the scope of this talk, but it works well in the Bayesian situation. So that's why this is a important distribution. Now, so if we want to talk about it being a distribution, the very first thing we should probably do, is to do the following. So question, how do you know that if you take this is a constant, or you can think about it as a normalizing constant, and you integrate from 0 to 1, this PDF right here, this density function, so how do you go about proving that? Now note, it's in theory, it can be a very messy integral, but for integers, alpha and beta, it's conceptually not that bad. Although you can see it being a pain in the neck where if alpha and beta have any magnitude to them. But the question, what I would call the hard part is, what about non-integers? That's what makes the case interesting. And it turns out what our proof will, of course, apply to integers as well. But so what we'd like to do, what we need to show, and this is where the prerequisites are going to come in, we need to show that if you take the gamma function of alpha plus beta, multiply it by that, what's known as a beta integral, you get the product of these gamma functions, or these gamma. That's what we need to show. So the classic way to do this is to start on this side right here, is to write, make this a little colon. And in fact, that's a very lousy looking right here. So let's just get rid of it. The classic way is basically to work on the right-hand side. So what I'm going to do is I'm going to start with this gamma of alpha, gamma of beta, and use the definition. And I'm going to choose x here for this parameter, dummy variable. So this is going to be x to the alpha minus 1. All right, e to the minus x dx. And then I'm going to, for the beta one, I'm going to choose a different dummy variable. Y to the beta minus 1, e to the minus y dy. Okay, so that's just using the definition. Now what we see, and this is the first part we're going to use two variable calculus, is that the product of these integrals, where this is integrated over the real line, half line 0 to infinity, this is 0 to infinity. This integral here can be now written as a double integral. And I'm going to go ahead and integrate with x second. I call that using dx slices. So this is x to the alpha minus 1, y to the beta minus 1, e to the minus x, e to the minus y, dy dx. And notice this is an integral over the first quadrant, where this is the x-axis and this is the y-axis. And we're integrating this function here over this entire plane. I mean, entire quarter plane. Quadrant 1, to be precise. Okay. Now, the next thing I can do here is I'm going to rewrite this integral slightly. Like so. I haven't rewritten any. I'm going to use this. This is e to the minus x plus y. I'm going to use that. dy dx. Now we do a change of variable. And what we're hoping is we're hoping to get this thing here to look like a gamma integral and this integral from 0 to 1. So that's sort of going to guide what we use to change our variable. Now, the person that came up with this is very, very clever. And if when we were doing our change of variable, we generally are going to want this to be one of our new variables. And then we'd have to be clever on how we choose our next variable. So what works? And I'm not going to give you a great deal of insight, but rather just show how the calculation works. And it, whoever invented this, they took it was a long, lot of work. What you use is you let x equal s times t. And you can see you're going to see in a minute why this works. Let your y equal s times 1 minus t. And note, and this is an important aspect, if you take x plus y, that's going to be st plus s minus st. So this x plus y here is set up to be s, which is going to actually do very well. That's going to set up the single gamma function that we have right here. So let's just put this away. Let's put this away. X plus y is s. So now we need to do the variable change. So to do the variable change. Oh yeah, and I should also. I jumped the gun just a little bit. So what's? Oh yeah, okay. I already said that's what y is. So now to do the variable change. We need to calculate the Jacobian, which is going to be the absolute value of the determinant of the partial of x with respect to t, the partial of x with respect to s, the partial of y with respect to t, the partial of y with respect to s. So I need to take the determinant of that and take the absolute value. So to find that, and if you're new to this, think about when you did polar coordinates in calculus. Your dy dx became r dr d theta. Well, we're doing something similar here. So the partial of x with respect to t, calculating Jacobian, partial of x with respect to t is just s. The partial of x with respect to s is just t. The partial of y with respect to t, well, you multiply this. Remember, this is going to be s minus st. So the partial of that with respect to t is minus s. And the partial of that with respect to s is 1 minus t. You take the determinant, that's going to be multiply here, it's going to be s minus st minus a minus st. And that's going to be s minus st plus st, which is going to be absolute s And we'll just go ahead and we're going to find out that your S is going to be positive anyway. So that's your Jacobian. So that's going to be the Jacobian for this change. Now, the next thing we need to do is now we need limits. And so this is where knowing a little bit of two variable integration really helps. So let's set up our XY axis here. And on this thing, let's set up our ST axis here. So on this side, I'm going to call this X and Y. And on this side, I'm going to call this T and S. Now, the very first thing to notice, because, and again, this just, remember X is ST, and Y is S1 minus T. And we also know that X plus Y is S. Now, the first couple of things that we notice now, if X is 0, that is, if we're along this y-axis, then S is 0 or T is 0. But if S is 0, Y would have to be 0 as well. So T equals 0 is what happens. So the X equals 0 line right here get mapped to the T equals 0 line right here. So we can really think that this axis here gets mapped like so. That's convenient. Now, if Y is 0, well, we know that if S is 0, then X must be 0 always, and that's not going to be the case. So if Y is 0, we know that T is 1. So this thing right here gets mapped to T equals 1. It's the image of X, of Y is 0, sorry. The image of Y equals 0. And then the other thing you note, if S is 0, okay, then X and Y are both 0. So the S equals 0 axis, this whole thing, this whole axis here, and I'll just put little dots around here, all gets mapped to the origin. So this thing here squeezes this segment on the t-axis. This whole segment gets squeezed to this point, and this t equals 1 gets the tail of this sort of turns and becomes this right here. So all of this stuff here is squished to that point. This line here, the t equals 1 line, becomes the x-axis. The next thing you notice is if you take the x plus y equals constant, that's a constant s, because remember, x plus y is s. So this x plus y equal alpha gets mapped to s equal alpha. So this line here gets mapped that way. And that makes total sense, because if you think about taking this tail of this ray, sliding that tail down here, as these things get compressed to the origin, you can see this tail sliding to be this x-axis, and this point here would become like this. Now, the other interesting thing is I have not solved for s. So let's solve for s. And because, I mean, solve for t. That's my bad here. We've already solved for s. Let's solve for t. So if you take x over y, which is st over s times 1 minus t, we get x over y is going to be t over 1 minus t. You know, I say, okay, that's great. Now you can solve for t very easily. So what you can do is you could say x over y multiplied by 1 minus t is t. Then x over y minus x over y t is t. X over y is t plus x over y t. And it's just a little bit of algebra. Like so. And then I'm going to go ahead and move in this direction here. I'm going to multiply both sides by x. I mean by y. So multiply this by y. Let me turn this into y. Multiply both sides by y. So you multiply this by y. It's going to be y plus x t. So x over y plus x is, we've solved for t. Now, what's interesting about that is if you look at the line, y equals mx. And so if you substitute that here, and remember what these lines are, this line's y equals mx. It's going to be something like this here. Well, if you take that line through the origin, substitute this in, then cancel the x, and it goes to that. So like when m is 1, t is a half. When m is 0, t is 1, which is what we already know. And as m goes to infinity, t approaches 1. I mean, approaches, I just re-embedded mathematics, 0. M goes to infinity, t goes to 0, and we see that already. So basically the vertical lines, a vertical line, vertical line approaches this. This thing here, this line there goes to this one, t. This is a line t equals 1 over m plus 1 for line of slope m. So now we see what's going on. We see how this works. So now when we go to our, if I can get back to our integral here. So let's go back to our integral. We're actually very close to being done. So I'll just rewrite the integral because I may have already forgotten it, but there we go. It's this right here. So x to the alpha minus 1, y to the beta minus 1, e to the minus x plus y, dy dx becomes, and this is where the thing is. The t, we now know that this whole quadrant 1 is being mapped to the strip between t equals 0, t equals 1, s goes to infinity. So our outer limit is 0 to infinity. And we have a ds. We have a dt. And then we have from the Jacobian this extra s. This is where this comes. Now we have an e. Remember, x plus y is s. That's good, right? Now, the x, remember, well, our t limits are t equals 0 to t equals 1. X is s to the alpha minus 1, t to the alpha minus 1. And let's see, let's give ourselves a little, this y here is going to be s to the beta minus 1, or 1 minus t to the beta minus 1. Now, what's kind of neat about this is you're starting to see this come into play. This part right here, this t, that's going to form our beta integral. And the stuff involving s is going to form our gamma, our gamma function. So let's just rewrite this and reorganize this just a little bit. Now this s to the alpha minus 1 times an s, that's going to be an s to the alpha plus 1 minus 1. There's a reason I'm writing it kind of a strange way. This is going to be an s to the beta minus 1, e to the minus s. Then let's look at the t. T to the alpha minus 1, 1 minus t to the beta minus 1, dt ds. Now take a look at this right here. This only involves a t. And, oh yeah, and I screwed this up here. I should mention that's 1. Sometimes I reinvent math. So that's a 1 right there. This part is going to be your beta integral. This involves an s. This involves an s. This involves an s. We can treat that as a constant and get it out of the integral sign. So let's just write in black 0, infinity. Now these two things combine to be s to the alpha alpha plus 1 minus 1. So it's going to be s to the alpha plus beta minus 1. That's good. E to the minus s. And that's we're just integrating with respect to s over this rectangles. Well, over this strip, which is a rectangular strip. And then now we have from here the stuff involving t. And the t stuff is t alpha minus 1, 1 minus t beta minus 1 dt. And look at what we just showed. We just showed, we just got what we wanted because this is now equal to, by definition, this is going to be the gamma function of alpha plus beta. And this is your beta integral. And I'm just going to change back to dummy variable. So our results proved, because remember at the very beginning, we started with this product of gamma alpha, gamma beta. So that is how you do the beta integral. Now, while we're at it, let's for grins, let's calculate. And I feel guilty doing this. So if you're a student, well, why don't you stop the video and see if you can do this yourself. So exercise 1. Calculate the expectation. Now the expectation is going to be, we'll start writing this down. It's going to be the integral from 0 to 1, y to the alpha minus 1, 1 minus y, beta minus 1, dy. Now, this is what's kind of neat here. This part right here, and we're not going to integrate much at all. Well, so much of stats is integrating without integrating. This is going to be the density function for the beta. This is going to be the beta density function where your alpha is really alpha plus 1 and your beta is just beta. So this thing, by what we just did, this is going to be gamma function of alpha plus 1, gamma function of beta, divided by the gamma function of alpha plus beta plus 1. And this is not going to be bad at all. Just use your definition of, not definition, but your calculational part of the gamma function. This gamma function right here is going to be alpha times gamma of alpha. This part right here is going to be alpha plus beta multiplied by gamma of alpha plus beta. And now we get some really cool cancellation here. So basically, this part cancels. This part cancels. And this part cancels. And lo and behold, what do we get? We get our expectation to be what we thought it should be. As expected. Okay. And I think we're out of this particular one, so I may as well say that. So we'll just call this beta 1. And let's do a new one. So what about, let's say, second exercise, what about the expectation of y squared? Well, that's going to look a lot of the same. It's going to be y squared, y to the alpha minus 1, 1 minus y to the beta minus 1 dy. But as before, this is going to be your beta distribution integral with alpha, the first parameter equaling alpha plus 2, and your beta part is going to just be beta. So we're going to get this right here. We're going to get the same cancellations that we got before. So this integral is going to be gamma function of alpha plus beta plus 2, gamma of alpha plus 2, gamma of beta. And that is not going to be too bad. We're going to use this recursive property for the gamma functions like we have before. It's a beta. Except this one's going to be alpha plus 1, gamma of alpha, gamma of beta. And the bottom is going to be alpha plus beta plus 1, alpha plus beta, gamma of alpha plus beta. And once again, we get some very cool cancellation. So we can say, all right, just cancel this guy, cancel this one. Let's cancel this one. And we end up with this kind of nice looking thing. So the expectation of y squared is going to be alpha squared plus alpha up top. On the bottom is alpha plus beta plus 1. alpha plus beta. Now, the variance, as you know, is going to be the expectation of that minus the expectation of y squared. Okay. And so let's just save our work for a second. All right. And let's see what we got here. So let's just do this. We take so let's just plug this in. So we got this. Then we subtract. And to remind myself what I did, it's going to be, and let's just look at our old stuff. And remind ourselves what we had. And that was alpha over alpha plus beta. Of course, this is now squared. So because do this, going to subtract this. And if we look at what we have here, it's good old common denominator. So we have alpha squared plus alpha. I need another factor of alpha plus beta to make that a square. That's an alpha squared. And I need an alpha plus beta plus 1. Now we have a nice common denominator. And what the heck do we have here? Well, it's going to be a little bit of a grind algebra-wise. So let's just do the top. So it's alpha squared times alpha is alpha cubed. Alpha plus that is alpha squared. And then we have plus alpha squared beta plus alpha beta minus alpha cubed minus alpha squared beta minus alpha squared. Oh yeah, that's a square there. And now let's just do the old cancellation again. This is additive cancellation. This goes away. This goes away. And this goes away. And we get our nice result. Alpha beta over alpha plus beta plus 1 and alpha plus beta squared. So that's going to be the variance of the beta distribution. That's what I have for today, and thanks for watching.